I'm so happy to be here with you today to talk about a junior challenge in quantum computing. Actually, a few years back, we decided that we wanted to go pre-university schools, either high school or CEGEPs here in Quebec, and basically to talk to students that are 17, 18, 19 years old and introduce quantum computing to them. We've been, of course, working here at the Institute on like big projects with industrial partners, and we've developed a lot of knowledge about quantum computing. But then we wanted to introduce this fantastic topic to younger students, and we decided that we needed a cool product, a cool tool to teach quantum computing. And this is what I want to talk to you about today. It's the Quantum Enigmas video series. Let's start right away talking about the first Enigma of the series. It's the first Enigma. You will see it in just a few seconds. The idea here is that there's no quantum advantage in using the Enigmas. The idea really is to use everyday life Enigmas. This one, you may have heard it before. And now ask ourselves, how is it possible to map this situation on a quantum computer? And then how is it possible to solve the situation on the same quantum computer? And this is the whole idea of the Enigmas. There will be some quantum advantage towards the end of the series. I can actually tell you that there's the fifth Enigma that we launched a bit before Christmas that actually do show a quantum advantage there. But for most of them, it really is classical Enigmas, and we see how we can have fun with quantum computers solving them. So what I'd like you to do is to open another window, and we will give you the link to this first Enigma. I will share my screen. It may work, it may not work, as we all know. And then if you want to watch the video just on the side, then you will probably have a better view and better sound and all of this. So I hope now you see the link in the chat. I think it's going to be shared, and we will all watch the video to the end. So let's start now for keep.
You are walking towards your destiny when suddenly you come across two doors. Behind one of the doors lies a treasure, but you don't know which one. There is a guardian in front of each door, and both know where the treasure is. One of the two guardians always lies, while the other speaks the truth. You don't know which one is lying or which one is telling the truth. Both guardians know which one is lying. Your challenge: ask a single question to one of the two guardians to find out where the treasure is. You can press pause to think about it or listen to the answer now. The question you should ask is, which door would the other guardian tell me not to open? Explanation: both of the guardian answers are always the opposite of each other if you ask, which door is the treasure behind? Or alternatively, which door is the treasure not behind? This statement is no longer true if one asks, which door would the other guardian tell me not to open? With this question, both guardians give the same answer, the right one. Let's suppose the treasure is on the right and the right guardian is lying. If you ask the one on the right, which door would the other guardian tell me not to open, he'll lie and answer, the other guardian would say not to open the right door. If the left guardian is asked the same question, he knows the right one is lying and answers, the other guardian would say not to open the right door. To translate this problem on a quantum computer, we'll need several quantum gates. The NOT gate transforms the state of qubits into their opposite state. The C-NOT gate uses two qubits, a control qubit and a target qubit. If the control qubit is in the one state, a NOT gate is applied to the target qubit. The swap gate switches the state of two qubits. Finally, the Hadamard gate places a qubit in a superposition of 0 and 1 states. The Hadamard gate creates a 50% chance of obtaining one state or the other, thereby allowing us to explore all possibilities in parallel. The two guardians know where the treasure is and are each assigned a qubit. To place the treasure randomly, let's use a Hadamard gate on Q0 followed by a C0 gate from Q0 to Q1 to ensure both guardians know the same thing. At this point, the probabilities of the treasure being on the right and on the left are in superposition. The qubits are simultaneously in state 00 and 11. If they were measured, or in this case, if they were asked which door the treasure is behind, both guardians would give the same answer. The two qubits are entangled. Since one of the two guardians is lying, we add a third qubit to the circuit for the lie itself. If the lie qubit is in state 1, the left guardian is lying and we invert his answer. If the right guardian is lying, we flip the right guardian's answer. By adding a Hadamard gate, the two possibilities are in superposition. There's a 50% chance of getting 0 or 1 for each answer. If you were to ask one of them, behind which door is the treasure, then the two would have opposite answers. Here are the 4 possibilities that describe the system. Either the treasure is on the right and the right guardian is lying, the treasure is on the right and the left guardian is lying, the treasure is on the left and the right guardian is lying, or the treasure is on the left and the left guardian is lying. The 4 possibilities coexist in parallel until the final measure is made. We want to ask, which door would the other guardian tell me not to open? To represent the statement, what would the other guardian tell me, let's apply a swap gate. Since we are asking not to open, let's also add a NOT gate on Q0 and Q1. Finally, keep in mind that one of the two guardians is lying about the other one's answer. As such, we must apply the circuit that changes the answer of the lying guardian with the same series of gates as before. Let's test this quantum circuit if the treasure was behind the right door and where guardian 0 lies. Here is how the system would evolve. Finally, we only need to ask the question to one of the two guardians to measure one of the first 2 qubits. We can measure the qubit of the other one to verify that we would have obtained the same answer. Interesting fact, we still don't know which one of the two guardians is lying, and Q2 is still in a state superposition. However, we can measure Q2 to determine which of the guardians was lying. We have just illustrated the first possibility, that is, the case where the treasure is on the right and the right doorkeeper is lying. Remember, unlike classical computers, the 4 possibilities coexist in parallel in a quantum computer until the final measurement is taken on one of the first 2 qubits. The set of gates works for all possibilities. Here is the distribution for the probability measurement if we run the calculation once. Each of the 4 possibilities has a 25% chance of occurring. Quick reminder, the qubits are noted in the following way for results. Qubit 0 is on the right, and the others are noted in turn to the left.
Great. So I hope it worked for you, either watching it with the subtitles or watching it in parallel. So that was the first Enigma of the series. And I told you it was a junior challenge here. So I have a question for you. And this is the question I'd like you to answer. You saw this algorithm in the video that, well, of course, the first half is mapping the problem, and then the second half is solving the problem, and then there's, of course, the codes that's sent to a quantum computer, and then the solution or the answer that is analyzed. The question I have for you is this one. Can you simplify the circuit? Because there's many doors or many gates here that can be taken off if you have the right logic there. I will give you 3 rules. You can, of course, take a print screen here if you want to have them in mind, because it's going to go fast through them. So there's the 3 rules I give you here that you can use to simplify the circuit. You may have noticed that I have the T-shirt of this first Enigma with the Quantum Enigma series here. And I will give a T-shirt to the 10th person that will send me an email with the right answer. So can you tell me how many gates are left at the end of simplification? If you give me the number of gates left to this email address you have here, we may put it in the chat as well so you have it easily. So the 10th person that gives me the right answer, we will send a T-shirt of the Quantum Enigma number 1 to you. So pretty nice challenge there. But then if you want to have more, what to do? As I told you, we have a whole series that's out with 5 enigmas, plus a intro video. The intro one, the required notions there, it's not really an enigma, but it's still part of the series to explain basically what are the quantum gates, what's a CNUT, what's a qubit, what's measurement. So we go all through these, but very quickly. If you have never heard of that before, it may be a bit too fast, but still, it's a kind of grocery list of everything's needed for solving the enigmas that come later. If you want to find all the enigmas, you can go to our webpage, quantumenigmas.com, or you can go to Quantique's YouTube channel, and you will find there all enigmas, both in English and French versions. And then if you want to have more still, and have more challenges there, you can go to the Qiskit problem sets that we worked with the Qiskit team. It's now on the Qiskit textbook. There is 4 problem sets for Enigmas 1, 2, 3, and 4 so far. And these problem sets are basically questions or exercises that we challenge you to solve. Using some Python coding, you will find a Jupyter notebook or equivalent there, and boxes in which you will put your code. You can grade your results and see how you did for every one of these challenges. So you can take a print screen here if you want to have access to all those QR codes and access directly all 4 problem sets that we have. So with all of this, let me tell you that we have 5 more Enigmas to come in the next year. Actually, the next one will probably launch in the next weeks from now. So you can go on our YouTube channel if you want to, of course, get notification when it comes out. If you liked the first Enigma, of course, I welcome you to give a thumbs up to it. If you want to subscribe to our YouTube channel, you can do it right there. And with all this, I guess that this is about the end of my presentation. Would you have questions for me on the quantum enigmas?
Thank you so much, Ghislain. That was really interesting to see. As a person with a background in science education, especially physics, public education myself, it's always interesting to see these sort of innovative approaches to that. I was wondering, before we get into the formal questions, if I could ask you very quickly. You say that you are into brewing cider. Is that correct? Can you tell us a little about that?
It is correct. Actually, I myself studied in geology. I've been a physics teacher, but then many years ago, about 10 or 12 years ago, I opened my own brewery, which I sold about 10 years ago. And now I'm brewing cider. And I'm brewing cider like for fun, not selling it at all. But I live in a region where there's many orchards around, and I can have access to like real fresh apple juice all the time, and in fall time, of course, but then just great juice to start with. And brewing cider is really fun.
It sounds delicious. Yeah, you'll have to share some with me sometime if I'm ever in the region. So we do have some questions about your talk here. I want to ask first. I found the sort of visual aspect really interesting. We've had quite a few talks already at QHack this year on the sort of more visual or design aspects. Was there some inspiration there that you can tell us about?
Yeah, I mean, that's the fruit of like many months of thoughts. Designing the Enigmas, it took about a year before the first one really was taking off. We wrote the storyboard, then we found a design motion company that is based in Quebec City that we work with. And with these people, I mean, great people, they wanted to jump into this creative work, not knowing what quantum computing was at all, or quantum at all. I mean, they had no prior knowledge of it. And they wanted to do this like creative project with us, and knowing that at some point in time we would tell them, okay, this and that we can do because it's scientifically okay to go there, but then there's this and that we won't go because we don't want to like jump into something like would be too confusing for people, and then losing track of what's real, what's not. So it took months basically to get the right colors, get the right characters there. Aika, it's not been named in the first video, but we named it in a later Enigma. Aika that you saw was a character very hard to come up with. We wanted it to be anonymous with no skin colors that exist. We wanted to have a female narration at the same time, so that we wanted to have like to interest girls and women into quantum computing more. And so there was many thoughts that we had. We wanted to all of this, and at the same time having a composer that would be liveful and that would be appealing. All of this was like a lot of work, but at the end, we're very happy of the results with all of this. And then it just grew from there, because I mean, this is the number one. Then with number 2, 3, and 4, the studio we worked with, I mean, they were so delighted to just push further and further at each time. I mean, I can't wait for the 10th to come, because it's going to be amazing. I can't tell you.
Absolutely. Yeah, you should give yourself a free t-shirt if you get to the 10th one, right?
Yeah.
we had some questions about the t-shirts, whether people can get them other than through sending you an answer. Are they available on your website?
Oh, that's a good question. Well, you can write to me to this same email address I have, and I mean, I guess we can figure out how to ship it. I have no idea how much it would cost. So, I mean, the T-shirt itself is $25, but then how much would it be for shipping? I have no idea. So, write to me, and we'll see what we can do.
Awesome. We did have another question from the audience. Just wondering, how do you come up with the enigmas? It seems like it wouldn't be an easy task.
Oh, that's a great question. You can't imagine how many enigmas I've read over the past 2 years on the web. It's in hundreds of them. And well, good enigmas for quantum computing, there is many scenarios in parallel, as you have in this one. There was 4 possible scenarios with the treasure either on the right or on the left. Then the right or the left guardian was lying. So 4 different scenarios. And it's the idea here, if you want to use parallelism that is in quantum computing and that is very distinct from classical computing, then you have to have scenarios in which this is the structure of the problem you face. Even though it's classical, you have to have this possibility. And finding that was not easy task. Well, I invite you to go watch the other ones. You will probably find a trend and some common aspects between them, and maybe you will not, and then it's also all right. And then when we had good scenarios, the idea was to map it on the composer. And I can tell you, there's one that was great, a great enigma, but so complicated with the composer of, I can't remember, something like 15 qubits or 20. And it was so deep in terms of number of gates there, it was just impossible. And I wrote the entire scenario, and then the rest of the team said, Ghislain, you know what, good effort there, but I mean, we won't make this one. I mean, it's way too complicated to get something between 6.5 minutes and 8.5, I think is the longest one of the series. And then it was just, okay, so we just flushed this one. It's bad, but I mean, we came up with just better enigmas afterwards. So it was great as well to go this way.
Yeah, it sounds like quite the process. Well, listen, thank you so much for being with us. I can see there's some questions that we didn't get to, but folks, if you have more questions, Ghislain will be available in Discord, so you can take your questions there, and go watch those videos. And thank you so much, Ghislain, for being with us this morning.
It was my pleasure. Okay, let's meet on Discord then.